So far we've talked just about static fluids, but a lot of fluids are actually moving. So today we're going to start talking about fluids in motion. We're going to talk about things like volume flow rate, about velocity and pressure in moving fluids, and about an idea called the Bernoulli effect. So first, let's talk about the two types of flow. There is smooth flow, or what's called laminar flow, where all the molecules are lined up and flowing neatly in a line. But above a critical speed, we have flow that becomes turbulent. And turbulent flow has these eddies, or the kind of the rolling back on each other of the fluid. And this is chaotic, and it breaks down some of the ideas we're going to talk about today. So today we're going to restrict our conversation to fluids that only move in streamline flow, fluids that are incompressible, so even gas molecules and wind, we're going to talk about it as if it's incompressible. And finally, we're going to pretend that fluids don't have any viscosity to them and no internal friction. This is important because when fluids move through things like pipes, in fact, the velocity of the fluid is not constant. The fluid is moving fastest actually in the middle of the pipe and very slow or almost not at all on the edges. This is really important in the human body with blood and arteries. In fact, the blood flow along the artery wall is very small, and that's why you get deposits of plaque along those walls, which causes thinning of the arteries and is a problem with heart attacks. But we're going to pretend that doesn't happen today as we talk about moving fluids. First, let's define what the volume rate of flow is. Volume rate of flow is just that. It's the amount of volume that flows per unit time. The units, therefore, being the volume unit, meter cubed, over seconds. If we think about what's happening in a pipe, we have fluid moving through this pipe. So the volume rate of flow, right, would be the volume that moves in that pipe per unit time. But we can think of it actually in terms of area and distance, right? The volume, in fact, is the area that the fluid moves through and a distance, right, per unit time. So we can rewrite our rate of flow equation. Instead of volume over time, we can also write it as an area times a distance over time. And if you remember back to kinematics, right, when something is moving at constant velocity, then velocity is distance over time. So I can replace this distance over time unit with velocity. So I have another way to calculate rate of flow. I can calculate it by collecting a certain volume per unit time, but I also can take the area of the pipe and multiply by the velocity of the fluid flowing through it.
I have water flowing out of a hose. What did I just do to make it do this?
Now, I'm sure that if you've ever played with a hose, you've done this, right? You were maybe wanted to squirt your friend, and so what did you do? You put your finger over the opening of the hose, and now the water went farther. Why did it go farther? Well, if it went farther, that must mean it's going faster. Right? Now, this actually is supported by this equation, the volume rate of flow, which says that in an incompressible fluid, the volume entering the tube, right, has to be the same as the volume leaving the tube. Therefore, the velocity is going to increase as the cross-sectional area of the tube decreases. Right? And our other equation for volume rate of flow was area times velocity. Right? So if I shrink my area, that means that in order to compensate for that decrease in area, the velocity has to increase. This actually is an equation that has a name. It's called the equation of continuity. The equation of continuity says that the area in one section of pipe times its velocity is equal to the area in another section of pipe times its velocity. And this comes from the fact that the volume rate of flow of an incompressible frictionless fluid in a pipe has to be constant. Let's take a look at a type of problem that uses the equation of continuity. Here I have a hose that has a 2 centimeter diameter when the velocity of the fluid is 4 meters per second. If I want to, say, squirt my friend some distance away, and I did some calculations, and I need that speed to be 15 meters per second, well, what does the diameter of this nozzle have to be? Well, if we go to our equation of continuity, right, area, which for a hose would be a circle, right, pi r squared, or pi d squared over 4, times the velocity has to equal the same thing in the other part of the hose. Well, if they both have pi, right, and if I use diameter, since I'm talking about diameter, that would be d squared over 4. Since those are on both sides of the equation, I can cancel them out, and I can move my equation of continuity to this. The velocity times the diameter squared in one part has to equal the velocity times the diameter squared in the other part. So remember that area is square, whether I'm using radius or diameter, it's squared. So if I plug and chug now, I have 2 squared, and I don't have to change units since they'll be the same on both sides. 2 squared times 4 has to equal 16 times d squared. Well, that's easy. 2 squared is 4 times 4 is 16. Right, divide by 16. That gives me 1, and the square root of 1 is still 1. So my diameter is 1 centimeter. Now, this equation of continuity, this fact that I have this speeding up as I move into a smaller section and slowing down as I move into a bigger section, right? You take your finger off the end of the hose and it slows back down, means that I have acceleration, right? In order to speed up or slow down, there must be acceleration, which means there must be an imbalance of forces. Well, where are these forces coming from? It's coming from the fluid pressure, right? Pressure is force times area. So I have this imbalance of forces caused by the pressure of the surrounding fluid. If I have this imbalance, right, then I get acceleration either speeding up or slowing down, depending upon if I'm going into a bigger or smaller section. And interestingly enough, right, if I speed up going into a smaller section, that means the force has to be higher on the bigger side, which means the pressure has to be higher on the bigger side. So in order to accelerate that fluid, the pressure has to be higher in the wider part of the tube, which is the slower part of the tube. Now that almost seems counterintuitive, right? You think, well, I'm putting my finger over the hose and I'm making it go farther so it's speeding up. Doesn't that mean I increase the pressure? Well, in fact, it's the exact opposite. We're going to talk some more about class. I actually have a really good demo for this. But if I speed up, right, I have to have a higher force in the bigger section of tube. So the smaller section, which has the faster water, in fact, has the lower pressure. Like I said, that's counterintuitive. So that's one thing you're going to want to remember. Now, the fact that the pressure is higher when the fluid is moving slower and lower when the fluid is moving faster was actually something that was discovered by Daniel Bernoulli and is called the Bernoulli effect. The Bernoulli effect is awesome. It's got some really great applications, and you can verify it by using this thing called a Venturi tube. A Venturi tube is a pipe here that has 2 different diameters to it and these vertical open pipes in each section. And you can see here in the slower moving part of the tube where we have that higher pressure that the liquid up here is higher, because remember in static fluids the fluid pressure is rho GH, right? So where I have higher pressure, I'm going to have a higher height like I have in that section of tube. But when we move into the skinnier section of tube where I'm moving faster, we can see visually that we have lower pressure because the height in those vertical tubes is smaller. Now, like I said, there's some really great applications of the Bernoulli effect. One of my, I think is the most interesting, is in tornadoes or hurricanes, right? We always think that the roof is being ripped off by all that wind, but in fact, as the wind moves across the surface of the house or the building, right, it moves faster. And if it moves faster, right, that means I've created lower pressure. And if the pressure is lower than what's inside, right? Inside is atmospheric pressure. It wasn't what it was before the wind started blowing, right? That means that the pressure inside is pushing the roof off. So in fact, the roof gets pushed off, not ripped off. In class, we're going to talk about some other great applications of the Bernoulli effect. So I'll see you in class.